I don't expect you to be able to remember that from its formula, but you can see it's containing nothing but molecular nonmetal elements, right? So it's carbon, hydrogen, oxygen, and hydrogen. The formula is telling us that you have 2 carbons, 5 hydrogens, and then there's an oxygen hydrogen group hanging off. That's the structural information that's put in there. Like if you've been reading chapter 3, you know this already. And this happens to also be another molecular compound, right? Now, if I were to change that C2H5 into a metal, then I would have a metal hydroxide, which would make it an ionic compound. So, nomenclature, more than just names and formulas. Lots of stuff you need to know. If you can't differentiate between compounds in terms of molecular or ionic, you need to go back and read chapter 3 again for the first time, right? Those are the things you have to do. Molecular, got people answering questions. Good. All right. Okay, what about those polyatomic species? How do they work? Well, they're a combination of both ionic and molecular compounds. Okay. Now, when we talk about polyatomic anions, we're going to learn how they work. Okay, we'll find out that polyatomic anions are just molecules that have an overall charge. So in the case of carbonate, right, CO3 2 minus, we'll see that there's 2 extra electrons somehow in that molecule to make it stable. If I talk about ammonium, NH4+, we'll see it's missing an electron to give it a +1 charge overall. So we'll learn all about those things down the road. For now, what you need to understand is a compound like copper 2 carbonate, right? Remember, that's just not copper carbonate, that's copper 2 carbonate. I know it's copper 2 because carbonate's -2, and there's 1 copper, so it's got to be +2. It's going to exist of a copper cation, right? So that's a copper atom that's lost 2 electrons, and a big old round hunking thing that's -2 charge that represents the carbonate. So there's an ionic bond that exists between the copper and the carbonate, right? So I would call this an ionic compound. But within that ionic compound, there actually are some covalent bonds. It turns out that the carbonate anion has structure, and it looks like this. You got a carbon at the center, 2 oxygens, and then a double bonded oxygen. Right? It's got a -2 charge overall. So we treat the overall thing as -2 and an anion, but it's stuck onto that copper cation through an ionic bond. So this is an ionic compound, but inside there are covalent bonds. Does that make sense? Okay. Again, you have to go look at the meaning of what's going on. So polyatomic anions are molecules that have a charge. So there are covalent bonds within those polyatomic anions. The forces that hold cations and polyatomic anions together, though, are ionic bonds. Okay? All right. Again, read chapter 3 again for the first time. Promise me you're going to do that. So when we talk about a formula now, we can break it down in what we call its empirical versus its molecular formula. Now, when we talk about the empirical formula of a compound, that represents the simplest ratio of each element in 1 mole of the compound or molecule, right? So regardless if I'm talking about a compound or a molecule, there's going to be a simplest ratio of atoms in that particular compound, which means we're going to get to a point where we can't divide through by 2. So if I have the compound C2H5O, all right, can I simplify that without getting into fractions? Well, the answer is no, all right? This formula can't be simplified because I'll end up with a fraction. If I were to divide that by 2, I'd end up with C, H2.5, O.5. And remember, we cannot have fractions as part of a chemical formula, right? So this is an example of an empirical formula. Now, a molecular formula, it turns out, is a multiple of an empirical formula. So if I can take an empirical formula and I multiply it through by a whole number, an integer, that gives rise to what we call a molecular formula. All right. So let's say I have the chemical formula C4H10O2. Now that represents a molecule. In that molecule, there are 4 carbons, 10 hydrogens, and 2 oxygens. In that molecule will have those hydrogens, oxygens, and carbons distributed in a certain way that give rise to a chemical compound. Well, it turns out there's more than one way to put them together. That's why the whole class of organic chemistry came about. I can take 4 carbons, 10 hydrogens, and 2 oxygens and probably put them together in a dozen ways to make a dozen different compounds. They all happen to have, though, the same chemical formula, right? So additional information is needed to identify a compound other than the formula, right? But one of the first things we do to identify a chemical compound is to look at its empirical formula, and that is a division or a simplification of the molecular formula, right? So if I divide this by 2, i.e. multiply by half, I see that the empirical formula for C4H10O2 is C2H5O, okay? So the empirical formula represents the simplest ratio of the elements in a compound. The molecular formula is a multiple of that empirical formula. Right? Again, reading from chapter 3. Now, for some compounds, the molecular formula is a multiple of the empirical formula. And so, let's say I have a compound that contains carbon, hydrogen, and oxygen, where X, Y, and Z are the subscripts, right? So 1, 2, 3, 4, and so forth. If I take that empirical formula and I multiply it by an integer, that integer will distribute itself throughout the formula such that I end up with a molecular formula that is CNX, HNY, and ONZ, right? You can see that it's distributed all the way through. Now, since the formulas are multiple of one another, then their molar masses should scale accordingly, right? Right. So if I have, let's say, a molecular formula, and that molecular formula is a multiple of the empirical formula, then that N factor must scale the same in terms of the molar masses of the empirical and molecular formulas, such that the following is true. If I take the two formulas, right, and I take CNX, HNY, and ONZ, and I divide it by CXHYOZ, I get N, right? Makes sense, right? If it's 2, I'd get a 2. If it's 3, I'd get a 3, and so forth. Well, that also means it should scale with the molar mass of the compound, right? The molecular formula mass divided by the empirical formula mass. They have to scale the same way. Right? And so if my molar mass for a compound is twice that of my empirical mass, then N equals 2. If it's 3 times N equals 3, and so on and so forth. So when we look at a chemical compound and we determine its empirical formula, we can subsequently then determine its molecular formula through additional experiments. If we take the ratio of those two molar masses, molar versus empirical, we get the scaling factor, which allows us now to take the empirical formula and determine the molecular formula, right? Because remember, the molecular formula is just a multiple of the empirical formula. Got it? Okay. So we're going to do some examples on how that works coming up. So understanding what an empirical and a molecular formula is, what they mean is important. And where do you get that information? You read chapter 3, right? So if you haven't read chapter 3, please, again, go back and read it again for the first time before you attempt the homework. I'll be setting up or posting the week 3 homework pretty soon. So those of you that want to get started on it, I'll have it available so that you can start it, I'd say on Thursday or something like that, okay? All right. So let's talk about a chemical formula in terms of the mass percent. Remember, percent is per what? Per 100, right? So the mass percent of an element in a compound is basically taking the total mass of the compound for 1 mole and then of one component of the compound in 1 mole of the compound and multiplying by 100, right? So it's like taking a ratio. So if I find out the amount of one substance per the whole substance and multiply that by 100, I get its percent. And I do that for the next and do that for the next and so forth, such that all of the individual percentages must add up to 100% when I talk about the whole compound. So let's say I have a compound that's N2H4. Okay, how would I name that? Say 2 nitrogens, 4 hydrogens, so that would be dinitrogen tetrahydride, right? This compound actually has a common name called hydrazine, but you don't need to worry about that, right? So it's N2H4. So in hydrazine, I have 2 moles of nitrogen for every 1 mole of hydrazine, or dinitrogen tetrahydride, right? I got that from the chemical formula. Now, since moles scale with molar masses, I could say 2 times the molar mass over 1 times the molar mass of hydrazine, right? Sure. Remember, moles are proportional mass by molar mass. So if there's a 2-to-1 ratio for nitrogen to the compound, then there's a 2 times molar mass ratio for 1 molar mass of the compound. Does that make sense? Right? Good. Everything scales. So to find the percent, we simply multiply that ratio by 100, right? So to figure out the mass percent of nitrogen in the compound, I would simply take 2 times the molar mass of a nitrogen atom not a molecule, a nitrogen atom, 14.007. And then I would take it and divide it by the molar mass of dinitrogen tetrahydride, right? And I'd calculate that, and then I'd multiply that number by 100, right? And then to figure out the the percent of hydrogen, I could simply then subtract from 100 because there's only 2 elements in the particular compound. Or I could follow the same calculation and take 4 times the molar mass of hydrogen divided by 1 times the molar mass of the hydrazine and multiply it by 100. Follow how that works? Okay, again, reading from chapter 3. So once you know the percent of one element, you can find the percent of the other. If there's only 2, if there's 3, then you have to find the percent of a second and then subtract to get the third, and so on and so forth. Okay? This is how we find the mass percent. So for example, let's figure out what's the mass percent of chlorine in C2Cl4 F2, right? So this is a freon compound here, right? Depending on how the chlorines and fluorines are distributed, it would have a complicated name, right? So this would be tetrachloro-difluoroethane. You don't need to know that. Don't worry about it, okay? All right, so to figure out the mass of the chlorine, mass percent of chlorine, I would simply take 4 times the molar mass of chlorine divided by the overall molar mass of the compound and multiply by 100. Well, that's easy, right? Yeah, so something that's very simple to do. Okay, I would look up the molar mass of chlorine on the periodic table. I would calculate the molar mass of the compound, 2 chlorines, 2 carbons, 4 chlorines, and a fluorine, and then I'd multiply by 100. Push buttons on my calculator. We would find out you would end up with 4 times 35.54 over 203.8 grams per mole. I just did it out to 4 sig figs here. Push buttons on the calculator with 100, and it comes out to be 67.58%. That makes sense too, considering chlorine has the highest number of elements, of atoms in the compound, and chlorine has the highest molar mass of all 3 of the elements, right? Carbon's 12, chlorine is 35, and fluorine's about 19. Okay, so to figure out the amount, the percent of fluorine, I would simply take 2 times fluorine over 203.8 times 100. To figure out the percent of carbon, I would take 2 times 12.011 times divided by 203.8 times 100, and so on and so forth. And all those percentages should add up to 100, right? The percent of chlorine, the percent of fluorine, the percent of carbon should add up to 100 because parts is parts and all adds up, right? Okay, good. I got questions in the chat. See questions in the chat. Other compounds. No. Okay, good. All righty. So the rest of the elements percentages can be found out in a similar fashion. How about we describe a chemical compound from percent composition, okay? Okay, again, our empirical formula, and this is what you need to remember. Empirical formula represents the simplest ratio of each element in 1 mole of the compound. So when you say empirical formula, simplest ratio, okay? Yeah. Okay, does that make sense? One method of determining empirical formula, all right, begins with a percent composition. Oh. So if I have the percent composition of a chemical formula, that will yield the empirical formula. Yes, it will. This is a classic problem that we do in chemistry. We'll use this a lot too. Even when you get to Chem 25 and Chem 24, and Chem 124 and 125, they still do percent composition calculations. You need to be able to do this. Now, the relative percentages of each element in a compound will then yield the subscripts in that compound, which are, in this case, for a compound that contains elements A, B, and C, the subscripts are X, Y, and Z. And in the empirical formula, X, Y, and Z represent the simplest ratio, right? So they can't be simplified any further. And again, X, Y, and Z have to be whole numbers. They cannot be fractions, right? Does that make sense? Okay, good. So if I know the percent composition for a chemical compound, then I can calculate the empirical formula, which yields the subscripts in the compound. Now, that's not necessarily the molecular formula. To determine the molecular formula, you'll need a separate piece of information, which we'll cover a little bit later in another calculation, all right? Let's do an example here. I happen to have a compound, and it was analyzed, and it's found to be 64.89% carbon, 13.59% hydrogen, and then 21.59% oxygen. So we know there are 3 elements in this compound: carbon, hydrogen, and oxygen, and we know that's it because the sum of those percentages darn well better add up to be, right? It better add up to be